Lecture 7-2, linear algebraic eigenproblem. So the linear algebraic eigenproblem can be simply stated for an n by n real matrix A. This is not necessarily the A matrix from the linear time invariant state equations. However, that's what we're going to use it for. We're going to introduce the eigenproblem in general, and then that we'll just apply it to the A matrix. So that's like a little foreshadowing. An n by 1 complex vector M, and lambda being some complex number. M is defined as an eigenvector of A if and only if it is non-zero, and this equality holds true for some lambda, which is called the corresponding eigenvalue. So let's take a little bit closer look at 711. It's saying that M is an eigenvector of A if its linear transformation by A is equivalent to its scaling by lambda. In other words, if an eigenvector of A is a vector of which A changes the length but not the direction. So typically when you have a vector, so like let's just put a nice little Cartesian vector out there, and you multiply that vector by a matrix, or you operate on it with sometimes it's just called a linear transformation. In general, you change the direction of that vector and its length. So like you could operate on it and it could become a longer vector or a shorter vector and in a totally different direction. Okay? So typically when you do this matrix vector multiplication, that vector not only gets scaled, it also changes direction. Now, an eigenvector then is a very special kind of vector for a matrix. So say you have that same linear transformation matrix, but instead of changing its direction and its length, it only changes its length. So it only changes the length of the vector. That's a special vector for that matrix, and it's called an eigenvector. That's what an eigenvector is. And like it has all these really special properties for that matrix. And that's why we use it a lot, because it has a lot of interesting properties. So a matrix can have several eigenvectors and corresponding eigenvalues. So we typically index them with a subscript. For example, m sub I pairs with lambda sub I. So whatever that scaling is the eigenvalue. The eigenvector is a vector that is going to get scaled and not changed, and then direction not changed. Okay. So solving for eigenvalues. So this is something that we should all be familiar with, but it's good to review a little bit. So 711 can be rearranged so that we have a subtraction from both sides of the AM, and we factored out I is the identity matrix here of the same size as A, and we have this result. And I don't prove this, but for a non-trivial solution for M, it can be shown that you need the determinant of lambda I minus A, whatever this matrix is going to be equal to 0. Okay? So that left-hand side, so this determinant, is going to be a scalar. It's going to be a scalar polynomial in lambda, and we're going to call this the characteristic equation. So 713 is going to be the characteristic equation. Wow, I'm using the same term that I use for the characteristic equation in the input-output ODE solution, right? The homogeneous solution requires a characteristic equation. And those roots of that characteristic equation were very important. We define eigenvalues to be the roots of the characteristic equation. So we're doubling up on the term characteristic equation, and we're doubling up on roots of the characteristic equation. We're calling them eigenvalues now. Interesting. Box 7.1 is going to unpack that a little bit. I did add this so that the box isn't in some of your notes if you printed them like at the beginning of the semester. So I liked the box because it just kind of like called out some stuff. So if A is taken to be the linear state space representation A, and the state model is converted to an input-output differential equation, the resulting ODE's characteristic equation would be identical to this matrix characteristic equation. So they're the same characteristic equation, that's why we're using the same name. So if you started out with a state space model, you converted it to an input-output ODE, and you found the characteristic equation, it would be equivalent to finding the characteristic equation using the formula in 713. And by the way, it's a lot less work. So that's pretty sweet. Good. So therefore, everything we already understand about the roots of the characteristic equation of an IO-ODE, which is a lot, and I'll highlight two specifically, especially that they govern the transient response and stability of a system. We explored that in detail. Remember, like the real part of the roots of the characteristic equation determines stability. And so the real part of the eigenvalues determines stability. Okay, so everything we know about roots of the characteristic equation, we now know about eigenvalues, which they were very key in stability and then also in the transient response. What does that response look like? Are those eigenvalues or roots of the characteristic equation, are they complex? Are they real? Are they positive? Are they negative? What's gonna happen to the response due to them? So all of that still holds, and now we can recognize that the eigenvalues of the A matrix are those values. Cool. So all that holds for a system's A matrix eigenvalues. Here we continue or we consider only the case of n distinct eigenvalues for eigenvalues of algebraic multiplicity greater than 1, which we call repeated roots in the characteristic equation. If we want to explore that, there's an advanced topics appendix at the end of the text that has a little lecture on that. It's a bit more complicated to do the diagonalization that we're going to learn about in 7.3. There is no strict diagonalization. There's Jordan normal form, it's called. And it's a little bit more advanced, so we skip it in this class, but a second pass through at a more advanced level, at like a graduate level, for instance, you would do that as well. But we're going to just treat that as being something that is a fringe case that we're not going to consider, but we know it's possible to consider them. We're going to focus in this class on systems that have A matrices with n distinct eigenvalues, which is most systems, so it's good. All right, we'll come back and do the example on Friday.